Don't put those over there. Don't put them right there.
All the faces.
I know. Don't you want other people to have
Hi. You guys see this work? Play the key.
Numbers are hard.
That's actually the most important person.
Speak up if you're not here.
All right, so this is Michael's thesis defense, so thank you for coming. So the process for this will be Mike will do his thesis defense. Feel free to answer questions if you want in the middle. What we'll do is we'll open it up for the audience to ask questions, then we'll have the thesis committee ask questions, and then we'll have a private session with just the thesis committee in the room. Okay? Right?
All right, so good morning, everyone. All right, so today we'll talk about smartphones. So these devices are everywhere, and they are really tiny supercomputers. And whatever they lack in terms of raw computation power, they make up for it through a whole range of sensors and connectivity options that are there on these devices. And researchers and developers have been developing many different applications using these capabilities. For example, researchers have used the cameras on the phone to track vaccine usage in sub-Saharan Africa. Or people post photos using their phone's camera of civil movements and revolutions. Or you can use the phone's GPS to track the spread of some infectious diseases. Or you can simply use the sensors to make sure that we are getting effects. So I don't think there is any doubt. I don't think anyone would debate that these sensors and these devices are useful. I think we all agree on that. But the question is, can we do something more? Can we teach these sensors some new tricks? Can we enable new applications that these sensors were not initially designed for? And if you think about it, many of the sensors on these devices are actually quite generic. The kind of things they can sense is light, sound, motion, touch. Those are some of the things that we humans can sense. And considering the amount of stuff that we can do, I think there is a lot of untapped potential in these devices, and we can really start leveraging their capabilities. And one very simple example of the kind of applications we can have are these heart rate sensing apps. So how many people here have used these kind of apps, or at least are familiar with them? So I see actually most of the people in the room have used the apps like that. But for those who have not, the way they work is you basically put your finger on the camera, and then basically the device shines the flashlight into your finger, and it tracks the change in brightness of the finger as the blood pulsates through it. And from that, it gets a pretty robust estimate of the person's heart rate. Now, from a computer science perspective, that's a very simple implementation. Like, you can probably implement it in like 2 hours. But once you implement it, you can have it on all of these devices, and suddenly every single device that is out there can be a heart rate monitor. And that's especially powerful because no one is going to distribute a billion stethoscopes in the world. But companies like Apple, Samsung, Microsoft are going to make billions and billions of these devices. So you can really begin to expand the kind of impact that these devices have. And I believe that my thesis is a step in that direction. And the thesis states the capabilities of generic sensors on mobile devices can be extended to enable applications that traditionally require dedicated sensors. And in presence of noise and uncertainty, multiple generic sensors can contribute to enable robust and deployable sensing systems. And that's a lot of words. The basic stuff, the basic thing that I'm saying is that the sensors that we have on our phones and other mobile devices, we can extend their capabilities for new applications. And when we deploy those applications, there will be situations when the environment will be noisy and there will be a lot of uncertainty. And that's when we need to incorporate the use of a lot of other sensors that are there on the phone to mitigate some of those challenges. And the sensors that I'm going to focus on in this thesis are the sensors that basically mimic the human capability. So the camera, microphone, the inertial sensors, accelerometer and gyroscope, and the touchscreen. And the reason I focus on these sensors is because they mimic the human capability, and there is that potential that we have not leveraged yet. And at a high level, the two things that I want to achieve in this thesis are, one, improve the stuff that the phone can already do so that we make it more efficient, and second, enable new applications. For example, I've looked at how we can use these sensors to make our interactions more efficient. On an average, we spend 2 to 4 hours every day using these devices. And if we can improve the efficiency of those interactions, so even if we improve the efficiency of these interactions ever so slightly, that can also have a huge impact. And secondly, I have spent a significant portion of last 5 years in developing and deploying solutions that use these on-device sensors for health sensing. If we enable health sensing on phones, I think we have a real chance to bring healthcare into the hands of the individuals themselves, and also lower the access barrier to medical sensing and medical technology in low-resource environments. And some of these projects are actually in process of FDA clearance and are used by hundreds of patients every week. Today, I'll walk you through some of my work in these two broad areas of interaction and health sensing. Let's start with interaction. And here, one of the areas that I focused on is this condition called situational impairments. So what are situational impairments? When we use these phones and tablets and other mobile devices, we don't use them at a desk. They're not like desktops. We use them in all kinds of environments. We might be walking, we might be in a cafe, it might be raining. It happens quite frequently in Seattle, and or we might be in a bus. But these devices are not aware of these changing situations, and they do not adapt to it. And that leads to inefficient device interactions that are called situational impairments. And one thing that I think everyone would agree is not that easy to do on a phone is typing on the phone. And this becomes even harder when you are walking or if there are a lot of vibrations. So I made a motion adaptive keyboard called WalkType, which derives inspiration from image stabilization algorithms. And I use the accelerometer that is already there on the phone to figure out how is the device moving and then stabilize for it by countering those vibrations and stabilizing the keyboard. So here I have data from the accelerometer when a user was walking, and this is basically acceleration along the x-axis. And once we pass it through a low-pass filter, and I collected data on like 20 participants, I saw that anytime this filtered signal went above the running mean, that indicated a right foot strike, and every time it was below the running mean, it indicated the left foot strike. Now, usually when we use these kind of things, we use them for step counting. And in that case, it doesn't matter whether it's a left foot or right foot. But it turns out for keyboards, it is important. When I looked at all of that data, I realized there was a pattern. Immediately after a left foot strike, let's say the user was trying to press the S key. In many cases, their touch drifted slightly towards the right, and they ended up pressing the D key. Similar thing happened in case of right foot strike as well, but in this case, the touch drifted towards the left. So basically what's happening is, immediately after a foot strike, when the vibrations are at their maximum, the touches drift towards the center of the screen. I leveraged this phenomenon, made some machine learning models on top of that. I am not getting into the detail of those machine learning models here, but when I compared the performance of this motion adaptive keyboard against a control condition, which was a static keyboard, and we looked at the error rate, and because this is error rate, so lower is better, you can see that WalkType reduced the errors to almost half. And this was really the first work that demonstrated that motion information can be used to improve typing on phones. But then I realized that motion is not the only problem. Ideally, we don't even want people to use their phones when they're walking, so why make it even better? And depending on the situation, we also hold the phones differently. Sometimes you might use it in your dominant hand, sometimes you are holding a bag, so you might have to use it with the other hand, 2 fingers, index fingers, all these different kind of hand postures. And the devices have no knowledge of that. The only thing they know is whether it's landscape or portrait. So they do not adapt to it. So I was curious to see what if the devices knew their hand posture. So I collected data with 16 participants and asked them to use the phone and type on it in different hand postures. And here you are looking at data from one of the participants when they were using the phone with the left thumb. At each key, you see a black line. The black line starts from the visual center of the key. So that's where the users were targeting to press. And the line ends at a circle, which is the centroid of the touches for that particular key. So you are seeing where they were intending to press and where they actually pressed. So you are seeing the drift. And because this is with the left thumb and the thumb has limited reach, so the user cannot reach the far side of the screen and the phones are getting bigger, so the touches drift towards the thumb. Similar thing happens for the right thumb as well. The touches are drifting towards the right thumb. In case of index finger, they are converging towards the bottom center of the screen. And in case of 2 thumbs, there is not much movement. And that makes sense because with 2 thumbs, you can reach all parts of the screen fairly easily. So considering there is enough difference in our typing behavior, how do we actually detect the drift? In past, researchers have added touch sensors to the side of the phone to detect how is the phone being held. But again, I wanted to see how far can we go using the sensors that are already there. And it turns out that the gyroscope is actually pretty good at this. Because the thumb has limited reach when you are using the phone with your thumb and you are trying to reach a part of the screen which is far away, your fingers compensate for it and they bring the phone closer to the thumb. So your phone rotates in a particular way and that rotation will be different for different hand postures. And in case of index finger, because there is no limitation of reach, the phone doesn't move that much. So you can build a pretty robust heuristic using just the rotation motion information that you are getting from the gyroscope. But you can make it even better. It turns out that when the user is trying to press a part of the screen which is closer to the thumb, the touch size is also smaller as compared to when you are touching the far side. And that's because when you are touching near, you are pressing with the tip of the thumb, and as you go far away, you touch with the pad of the thumb. So the touch size increases. And again, this will be different for the 2 thumbs, and in case of index finger, you won't see much difference. Another heuristic that you can add on top is the information from the swipe. The swipe has an arc shape that is very distinct for the 2 thumbs. And in case of index finger, there is no such significant arc in the swipe. So by just looking at the shape, you can get a robust estimate as well. And when you combine all of these 3 heuristics, the performance is very, very robust. I'll show you a quick video of the system in action. The user will be typing on this keyboard and the inferred grip will be shown at the top left corner of the video and also right above the keyboard where it says index right now. So the user is using with the left hand and the system detected that. So usually within 3 to 5 interaction steps, the system is able to lock and get onto the user's hand posture. And so now that we know what in what grip is the user holding the phone, the next question is, does that really improve typing? We saw that the typing patterns were different, but does that improve typing as well? So I made a...
The swipe, do you add something like an explicit swipe to the interactions?
Not for keyboard. But we have examples like people were scrolling through list or checking the emails. So I made a grip-sensitive keyboard called context type, and this was very similar to the control condition. It had a language model, it was personalized for each user, so it was as advanced a keyboard that was out there. But the only difference in context type was it had this 2-bit information about the grip, which of the 4 hand postures was the user holding the phone. And that 2-bit information, when we look at the error rate, reduced the errors by 20%. So the thing I wanted to show you here is that the on-device sensors can be used to make interactions significantly more efficient. But there is an interesting point here. The inferences are being used in the background. The visual interface is not really changing on the basis of these inferences. For example, the underlying keyboard is changing, it's stabilizing or adjusting according to the grip. So even if context type is wrong sometimes, the user won't really notice. So the system can afford to be wrong sometimes, and it can also afford to be delayed by like 3 or 5 interaction steps. Now imagine if the same inference was used to change some visual element of the screen, then the user would not like the noise, or they won't like the delay. But in this case, it doesn't matter, but it won't always be the case. And that brings me to the second part of this talk, health sensing. Here, I use the sensors that are there on the device to detect different diseases and physiological conditions. So here the penalty of error and delay can be much, much higher, but at the same time, the gain can be larger as well. Because if you are only using the sensors that are already there, we immediately bring healthcare into the hands of the individuals. They can just start using that medical device right away. And if we take the case of developing world, there are many places that lack basic healthcare facilities. I recently visited this clinic in Bangladesh, where patients come from as far as 100 miles away, just because that's the nearest option for them. And one thing that is common between developed and developing world, to a large extent, is the phone. More than 70% people in sub-Saharan Africa and South Asia have a phone now. And almost 15% of these phones are smartphones. So if we enable mobile phones to be used as health devices, we can definitely lower the access barriers to healthcare. And one area where it is really important to make health sensing more accessible is pulmonary diseases, lung ailments. These diseases account for roughly 10% of global deaths. That is 4 times worse than HIV/AIDS. What is even more unfortunate is that more than half of these patients remain undiagnosed throughout their lives. And the diagnosis is not the only problem. Most of these ailments are chronic, so once diagnosed, the patient needs to manage their condition throughout their life. So not only do we have to, we need a technology that can help them in diagnosis, but it should also help them in managing their condition. So currently the device that is used to measure the severity of lung impairments is this device called spirometer. And this device basically measures the amount of air inhaled and exhaled. Let me first show you a quick video of how this device is used. In this case, the spirometer is that big white box in the back. And at the start of the test, the patient takes the deepest breath they can.
Deep breath in. Keep it down. Push. Come on, Jordan. Squeeze. Squeeze all the way down. Stop. You can do a push all. And deep breath in.
So they take that deep breath and then they exhale all of that air out as fast as they can, and they keep on exhaling until there is no air left in their lungs. Exhaling until they don't feel that any air is left in their lungs. And at the end of the test, the system generates this graph, which is basically plotting the rate at which you exhaled versus the total cumulative volume of air that was exhaled. And the doctors and the pulmonologists extract different measures out of this. So let's look at this graph more closely. So the first parameter that we look at is peak expiratory flow, or PEF, which is basically the maximum flow rate that was attained during the test. The second is called forced expiratory volume in 1 second, which is basically the volume of air exhaled in the first second of the test. And the third one is FVC, or forced vital capacity, which is the total amount of air exhaled during the whole test. And then there are others which are basically looking at ratio of FEV1 and FVC, for example, but the sensing is basically looking at these 3 things, and from that you can extract a lot of different measures. And apart from these measures, it's also important to look at the shape of the curve itself. So like in this case, if you look at the descending limb, it's almost a straight line. So that indicates a normal lung function. In some cases, it can have a scoop shape, and that indicates an obstructive disease like asthma or COPD. And in some cases, the patient is unable to exhale as much air as someone of their age, height, and race should be able to exhale, and that indicates a restrictive disease like cystic fibrosis. So how do these devices measure that? At the most basic level, these devices are very precise pressure and flow sensors. So they are basically measuring the flow rate of air as the patient exhales. We enabled similar capabilities on a phone. We made an iPhone app that doesn't require any attachment or external sensors. The users simply hold the phone at a comfortable distance, and they exhale forcefully at the screen of their phones. And in the same way as they would blow through a conventional spirometer. And at the end of the effort, you get a similar flow volume graph as you would get on a clinical device. So it just uses a microphone that is there on the phone. But how do we convert a simple microphone into a precise airflow sensor? The basic premise that we started with is that the microphone is basically an uncalibrated AC coupled pressure sensor. I'll break that term down one by one. So let's look at the pressure sensor part.
Thumbs up.
So my time starts from 0 now. Alright, so it's basically a pressure sensor. So when the patient exhales at the phone, we are getting the pressure at the phone. And because we have a rough estimate of the distance between the phone and the user, we can figure out what pressure drop happens between the phone and the lips, and we get a rough estimate of the pressure at the lips. And because when the patient exhales, it's a turbulent airflow, we can convert that pressure at the lips into air velocity at the lips. It's a rough estimate, but we get a rough estimate of the air velocity at the lips, and that's what we were looking for. But it is still AC coupled and uncalibrated. So let's look at the AC coupled part. What that means is that when you look at the signal, it will have this high frequency component to it. One thing that we can do is we can just take an envelope of this and use that as our feature. So that forms the first class of features that we are using in our algorithm. The second approach that we take is we use linear predictive coding, or LPC, and we use that to basically figure out the source of the white noise that is generated when the patient exhales. And that forms the second set of features that we use in our algorithms. And the third set of features that we use is basically coming from resonance tracking, and that's using the human body as a transducer itself. When you exhale, your vocal tracts get activated, and the sound that your body generates changes. So it converts the airflow into sound. So for example, when I'm exhaling and I'm not exhaling too fast, you don't hear much. But when I exhale fast, like, you hear the reason that resonance. And that's because the vocal tracts are getting activated when I exhale really fast. So you can use that and figure out at least a rough estimate of the rate at which air is coming out of the patient's lungs. So that forms a third set. So those are the three sets of features. But the features are still uncalibrated. To calibrate this, we use machine learning, and all of these three features are then inputted into the multiple regression algorithms. We use random forests and conditional random fields, and different
now,
of these two algorithms. I'm not going into detail of that right now. And then from these estimates, we finally cluster them together, we take their mean, and generate the final lung function measure for all of the three measures that I talked about earlier: PEF, FEV1, and FEC. And in our tests with 200 participants, the app was almost as good as a clinical spirometer. The average error for these 200 patients. And the main thing to note here is that there is no real ground truth. When a person is using their phone and they're exhaling at it, you don't know how much air came out. The only thing you can do is you can ask the patient to do the test multiple times on the phone and on a clinical device, and hope that they put in exactly the same amount of effort in the two efforts, and you basically use the values from the clinical device as the ground. And multiple studies have shown that the variability within the same participant of around 5 to 10% is very low. So that puts at 6.2% in context. The performance was reasonable enough for us to scale up the study, and the fact is, like, for deploying it, because we are just using a microphone that is already there on the phone, deploying it is very easy. You basically send out the link to the app to people who are interested, and that's it. I'll get into the details of the deployments later, but first I wanted to go back to this graphic that I showed earlier, where I said that 15% of the phones are smartphones. What that means is that 85% of the phones are not. But those phones also have a microphone. Microphone is not exclusive to smartphones, and considering SpiroSmart is just using the microphone, we can actually implement it on all the phones in the world. It doesn't need to be a smartphone. So we made a call-in service where the user calls a 1-800 number. to do the test. And we actually tested it on a 10-year-old phone as well as on an iPhone. And our results showed that there was virtually no difference between the iPhone and the 10-year-old phone. And the challenge here is not just making the call in service and using the same approach as PyroSmart, because the audio signal goes through a lot of changes and it looks very different once it goes through the GSM channel. It might be slightly hard to see, but this is spectrogram from from one effort recorded simultaneously on 4 devices. The one on the left was when the effort was recorded on a phone that was recording it locally, so that mimics the PyroSmart approach. And the one on the right is when it was recording over a GSM channel, so that mimics the call-in service, the Spyro call approach. And it's a spectrogram, so the x-axis is time, y-axis is frequency, and the brightness at each pixel indicates the magnitude of sound at that time and frequency. So the first thing I want to do is I want you to focus on these parts of the spectrogram. And you can see that in the local recording, there are some bright spots. So basically, there is some data there, but there is nothing in the GSM recording. So a lot of data is lost. However, if we look at this part, the two spectrograms look fairly similar. They are different, but they are quite similar as well. And that at least gives us a starting point. And the first thing I did was I used the PyroSmart algorithms as is on this data. But the performance expectedly wasn't very good. But one thing that works in our favor here is that the GSM channels, when they compress the audio, they use LPC, linear predictive coding, for their compression. And that's 1/3 of the features that we use in our algorithms. So I made some changes to the regression algorithms to counter for the noise. I'm not going into that detail here. But I also increased the weights of the linear predictive coding based features because those features remained preserved. They were preserved more as compared to the other set of features that we had. And then to evaluate the system, we had participants used 4 different devices. 2 of these devices were recording the data locally, so that mimics the PyroSmart approach. And the other 2 devices were recording the data by calling in a Google Voice number and recording the data as a voicemail. And that mimics the call-in service approach because the data is going through a GSM channel before it's recorded. And the participants also used 2 clinical devices. And the reason we use 2 devices is because I wanted to understand what kind of variance exists between these devices so that we can set the right kind of expectations for our algorithms by looking at what is the difference, what is the variability between 2 already clinically approved devices. And if we look at the results, this is the difference between the 2 clinical devices. So there is like almost a 5% difference between the 2 on average. PyroSmart had a very similar performance. And SpyroCall, on an average, had slightly higher error, but the differences were not statistically significant. But more importantly, it's still within that 5 to 10% range that we have seen that the devices that the same patient can vary between.
You go back. So if you had no ground truth, how do you assess error for your clinical spirometer? So you're using the clinical spirometer as your proxy for the ground truth for the PyroSmart SpyroCall.
Yeah. So
how do you assess error with the clinical spirometer? Did you assume that one of your 2 clinical devices was the ground truth?
Yeah. So we basically looked at the order in which the 2 devices were used was randomized as well, because I didn't want to use the same device as the first device because fatigue can build in. And we saw a significant effect of fatigue. So in every case, I used the device that was used first as a ground truth. Okay, so by just using the sensors that are already there on our phones, we were able to convert it into a parameter. And hopefully we can reduce the percentage of undiagnosed patients that are out there. And currently the system is deployed in multiple locations in US, India, and Bangladesh. And we currently have a huge data set of more than 5,000 patients. And I recently visited this clinic in Bangladesh and they started collecting data for us in October last year. This clinic receives around 40 to 50 patients every day because it's one of the only clinics of its kind in like a 100 square mile radius. And they use a clinical device to check the patients. It's actually the same clinical device that we use in our studies. And when we first started, they said that, the 50 patients that we receive every day, we'll take 10% of these patients and we'll test them on SpiroSmart as well, so that we can use that as a comparison between SpiroSmart and the clinical evidence. And that sounded great to us. It took us 3 years to get 200 patients in Seattle, so getting 5 patients every day was like pretty good for us. But it turns out that the patients were not happy. The 45 patients who didn't get to use the iPhone app were like, we want to use it as well. So they demanded it, and now actually the clinic sends us data from all of the 50 patients every day, which is huge because it helps us in getting a lot of data. And if we look at this normalized spectrogram of the distribution of age of the participants, the blue one is from the initial study that we did. And barring some people, most of them are like, in the age group of 20 to 30. And that's not representative of the world. Maybe this room, but not the world. But the clinical deployments helps us, right? Because, actually, not this room. But yeah, the clinical deployments helps us in making sure that we have a pretty uniform distribution of age. And if you look at lung function, there as well, the blue curve. So here the x-axis is FeV in percentage. That's basically you can assume that around 0.6 is where the patient is around mild to moderately affected. So that's like we had some people who had that lung function in the initial studies, but the clinical deployments have really helped us in having a much bigger spread on the kind of lung function that we are seeing in data. Okay. So the next thing that I wanted to talk around this is some of the challenges that are associated with these deployments. And one of the biggest challenges is because the patient needs to make sure that they are taking their deepest breath and exhaling all of it out, and they don't stop in the middle of the test or they don't cough and all those things. And that's where Spirometry 360 is very helpful. So what's happening is that every single test that is being done on SpiroSmart goes into this database, and Spirometry 360 basically gives feedback to the patients on whether they are doing the test correctly or not, or what do they need to fix. So this is an example grade sheet that you see that the patients and the therapist would see on Spirometry 360. So this is the flow time graph for one of the patients, and then therapists look at these graphs and the numbers and they give them feedback. So the feedback is here where the therapist, Drew, has given it an 8 rate. Let's look at another curve. If we look at that flow time graph, that doesn't look like anything that I've shown you here. And in this case, Drew says, a lot's going on with this patient. It appears they didn't understand the maneuver. So now that kind of feedback is very important. You want to make sure that the patients get that feedback. Right now, it's not very important for SpiroSmart because it's used in clinics, but that's not the end goal. We want people to use it at homes, and when they use it at homes, they need to be trained properly. And when they use it at homes, because it's indirect sensing, there are a lot of other things that can go wrong. When you're using a clinical device, it has a mouthpiece, there is a set way of using it, you'll have the mouthpiece in your mouth and you'll exhale. When you're using a phone, you can make all kinds of mistakes. For example, you might not hold the phone properly. Usually when you're using SpiroSmart, you need to hold it like upright, and you need to exhale on the screen and not directly at the microphone. But this is a problem that can easily be solved with the gyroscope that is there on the phone. Similarly, let me play this audio for you of one of the recordings. So this is an example of the test recorded in one of the clinics. And this is again the spectrogram. So that's the part where the patient was the most had generated the most sound. And this is like people talking in the background. And that is the car horn. Honking in the background. That's pretty common in that part of the world. So when I was there, and like almost 30% of the efforts had to be rejected just because of honking and like that. So, but these are some of the things that might be hard to filter out, but at least detecting them is not hard. So we can easily imagine having the microphone detect some of these things and tell the patient that that was not the correct test, you need to do it. Some of these things are already built into the system, but like for example, like honking, because that will be a slightly different sound that is already built in, but I'm working on like incorporating detecting speech and telling the person that maybe someone is talking in the background. Another thing that we do is immediately before the patient exhales, when they inhale, that doesn't generate enough sound. So we can use that to figure out what is the ambient noise level. And if it's already too high, you can tell the patient to stop. Another thing that happens in a lot of cases is lip posture. When you're using a clinical device, you have a mouthpiece. So the lip posture is not important. But in this case, you don't have a mouthpiece. So it becomes important that you do not purse your lips. The user needs to keep the mouth open so that the airflow is not impeded at the lips. But in some cases, patients do end up pursing their lips. Right now, it's not a problem because it's in the clinic and the nurses and clinicians can tell them to fix it. But when they use it at homes, it is important. And there, we can use the combination of microphone and camera to detect things like that. You can easily imagine with the camera, you detect the lips and see if it's pursed or not. But the microphone can be useful as well. So this is the two-effort patient, first with the correct lip posture and then with the pursed lips. So if we look at this spectrogram with the correct lip posture and we zoom in, we see some resonances. That's what I was talking about earlier, that are resonances that are excited when the user exhales. And because the lip posture is correct and the airflow is not impeded, those resonances are there. When the lips are pursed, the flow rate won't be too high and you won't see any resonance. So you can always use the presence of the resonances as one of the features to decide whether that was a correct test or not. Another thing that might happen is a change of distance. Not everyone will use the phone at an arm's length. That's how we initially started. We asked everyone to put the phone at arm's length. But in some cases, people bring the phone closer to them, or in some cases, they just do not generate enough sound because they have really, really low lung function, that they just don't generate enough sound that can be picked up at that distance. In that case, then you need to ask the patient to bring the phone closer. So now the system needs to know how far is the patient. That's where the camera can help. So we basically we detect the two eyes, and we use the distance between the two eyes as the inverse proxy of the distance between the phone and the user. And once the user has done the test, the system takes a photo and converts it into a silhouette using the front-facing camera, and it can tell the user that what is the correct distance for them for the next test. So they can align their face into the silhouette. So this works well for SpiroSmart, but what about SpiroPod? It only has a microphone. So we cannot do a lot of these things there. And many of these things are there because we don't have a mouthpiece. So we actually made a smart mouthpiece, which is basically a whistle. It's a vortex whistle, and let me first do a test on it just so that you can listen what it sounds like. It might be hard to realize that, but the main thing about this whistle is that apart from changing the amplitude of the sound that it's generating when the flow rate changes, the pitch of the whistle changes as well. So this is the spectrogram from one of the tests, and you can see that the pitch goes up and then it slowly comes down. And that looks very similar to the flow time graph that we could get on a normal spirometer. So it's linearly proportional. The pitch is linearly proportional to the flow rate. And so we can use it as a direct measure. And if we look at the performance of this whistle and compare it to SpiroCall, the error was slightly higher. Again, it was not statistically significant, but more importantly, because the variability is less, the patients can use it more easily. If we look at the overestimations of lung function, so false negatives, without the whistle, there were 4 people who were false negatives, 4 of the tests, and in case of whistle, there was only 1. So the number of false negatives or overestimations can be much lower with the whistle because you remove a lot of this uncertainty. And in terms of challenges with the whistle, lip posture, of course, because you don't need to maintain that, you have a mouthpiece. Ambient noise is also not a big problem because you are using something that you know what it sounds like. And you are not relying too much on machine learning. When you use SpiroSmart without a mouthpiece or without a whistle, garbage in would result in garbage out. But with the whistle, you can have a slightly more controlled level. So that helps as well. And the phone not being held or the change in distance is also not a problem because the pitch of the whistle is changing. So it's not dependent on amplitude. So the frequency response of the phone or the distance, as long as the algorithm can figure out where the pitch of the sound is, that's all that matters. If it's not there, you can always tell the participant to bring the phone closer. Okay, so So at a more general level, the thing that I wanted to show here is that when you're using these sensors in this indirect sensing approach, there is a lot of unconstrained usage. So the sensors are very sensitive. They make the human capabilities. So they sense everything. They listen everything. They can see everything. So the chances of noise is much higher. And you don't normally run into these issues with dedicated sensors, not only because of the sensor design, but also because of the form factor. For example, in spirometers, you will have that mouthpiece, right? And this thesis talks about some of these issues and some of the steps that we can take to mitigate them in much more detail. But the next thing today that I wanted to talk about is evolution of devices and their sensors. I think there is a need to go beyond the human capabilities. These sensors are already very powerful because they are mimicking our capabilities, but I think they can go beyond that. When they were initially designed, they were designed for documentation of human experiences, and I think we are way past that point now. We need to treat these sensors as real sensors and not limit them by our own perception. In a way, near ultrasonic frequency stuff that a lot of people have been doing for the last decade or so, around 18 to 20 kilohertz band and audio is an example of that. And I believe similar approaches are necessary for other sensors as well. And even for microphone, that was incidental. It's just that the hardware that was made to basically, cut off at around the human perception and had just ever so slightly extra at the end that people have been using. But I think we need to go beyond that because these are sensors and are not just used for documentation of our experiences. And one sensor that I think can benefit a lot by going beyond the human capabilities is the camera. And it is already a very powerful sensor. I worked with some of my colleagues in this room to detect a condition called hyperbilirubinemia. So this condition affects 84% newborns in the first week of their lives. And a major symptom of this condition is jaundice, yellow discoloration of the skin. Extreme levels of lifelong conditions. We made an app called BillyCam to detect these elevated levels of jaundice using the phone's camera. Currently, there are two ways to measure it, either with a blood test, which is a gold standard, or with this device called TCB, which is used as a screening tool. These two devices work really well, but they are in hospitals and clinics. And if you look at the increase in bilirubin levels, with respect to a baby's age, the level really peaks when the baby is around 3 to 4 days old, and that's when the baby is at home. So one of my lab mates, Eric Larson, who worked with us on this project, had a baby 4 years ago, 5 years ago, something like that, and so they had the baby, and after 3 days, they thought that the bilirubin level is high, and they took the baby to the hospital, and the doctors were like, yeah, it's yellow, but it's not too yellow. You don't need to worry about it. You can go home. And this happened for 3 consecutive days. And after 3 days, the doctors were finally convinced, and they treated the baby, and he was fine. But the parents had to deal with this uncertainty about their baby's health for 3 to 4 days. And that's where a phone-based measurement is a perfect example of bringing healthcare into the hands of individuals. If the parents could simply take a photo with their phones and check if they need to go to the hospital or not, that can be very helpful. Once they are in the hospital, they can do the blood test, but at least you can use the phone as a screening tool. The system is currently tested in multiple locations around the country, and we have data from around 500 babies. And here we have the scatter plot of the results. And so it's basically have the ground truth ESB readings, the blood test on the x-axis, and y-axis is the estimated bilirubin level. And we have data from TCB, the FDA cleared clinical device, and as well as BillyCam. So we are comparing the performance of the two devices, and they have identical performance. They both have a rank order correlation of 0.92. Actually, TCB has 0.915, but let's round it down. But we do have less number of false negatives. So at a higher range, TCB is known to have false negatives. So that's where BillyCam is slightly better than TCB right now. And but it's not as simple as simply measuring the yellowness of the skin. Apart from many other challenges, the skin tone is of course one very big confounding factor. But the point is that the phenomena is still visual. You can see it with the human eye, and so can the camera. However, there are many phenomena that do not exhibit visual change. For example, an avocado would look the same to the human eye. However, when you put it in front of a hyperspectral camera, it would look something like this. So this is a time-lapse video of a pair of avocados left in front of the camera, or hyperspectral camera, for a week. And this video was recorded using HyperCam, which is a low-cost hyperspectral camera that I worked on in collaboration with folks at Microsoft Research. The difference between the hyperspectral camera and the normal camera is that a normal camera basically looks at the red, green, and blue. And a hyperspectral camera looks at wavelengths, other visible wavelengths as well, apart from red, green, and blue, but it goes beyond that as well into the infrared and ultraviolet range. And the point I'm trying to drive across here is that the camera was very powerful, right? Like it can implement a thing like Wingcam. But there are so many other things that will happen outside that range where that camera won't be enough. And I think we need to take that camera beyond that. So the HyperCam, in this case, apart from red, green, and blue, has 13 other wavelengths. Some of them are in the visible spectrum, and some of them are in the near infrared. And what happens is it shines these lights one by one on the scene and records their observation. And there are a number of applications for such cameras. For example, tracking of wound acid fields. Different wavelengths of light would penetrate different depths into the skin, and that can really help us in understanding how the skin feels under that wound. And I'm also talking to some dentists right now, and they are interested in putting a small version of this camera into a toothbrush to continuously track that. And it's not too far-fetched. Like Edward actually just left the room, has already implemented a small version of a similar camera on a phone. So the overall point that I'm trying to make today is that the sensors on our phones are already quite powerful, and we have come a long way from the time when these sensors were only used for documentation of our experiences. The combination of clever use of existing hardware, like a lot of stuff that I've shown today, and evolution of this hardware will push the envelope further, and that will help us in expanding the impact of these billions of mobile devices. Thanks. Before I end, I want to say thanks to Gaetano. He's not there anymore, and I really do not have words. He was extremely supportive of everything I did, and I could not have done even 10% of the stuff that I've done in the last 5 years. He will always remain someone I look up to. And the work I show today is in no way just my own. There is nothing that I've shown today that was not done in collaboration with many, many awesome people, some of them in this room. And I just get by with a little help of my friends. All right, questions?
So I was wondering with the whistle, is it something that you could use independently of a smartphone to interpret? So is it something that could augment the signal so a clinician could listen to the whistle? And
that's a good point. I think if it's like a 3-class problem kind of thing, that is the person very sick or less sick or normal, they probably would be able to do that by just listening to it. But I think to get to the subtleties, it might be hard. But I think if you're looking,
but can you just modify the design of the vortex whistle so that it has 3 peaks where it has 3
that's what I'm saying.
pitches?
Like you can have some levels of granularity, but you won't get like one number out of it. Like by just it's similar thing happens in Wingcam, right? Like when they're tracking jaundice, the experienced doctors can just look at the baby and tell whether they need to get a blood test or not. So you can use it as a screening tool. So similarly, I think with the whistle, you can use the human as like a screening tool to decide whether they more complicated.
But that's an interesting point, right? So,
Yeah.
I mean, something completely mechanical could potentially be used as a screening tool.
Yeah.
What are your thoughts on that?
I think it can be used, definitely. Like, in some cases, you can just listen to the tests that are done on Spirosmart and I can tell you whether the person is sick or not. But I think with the whistle, it could be much, much better.
Is Jim in the room?
Yeah.
What do you think about that?
I think it's a great idea. It veers away from our software-only approach to this work, but the fact that it correlates so well with flow, how could you not pursue it?
Yeah.
So going back to the difference between Spiral Call and Spiral Smart, you're doing a lot of like error detection with Spiral Smart, but Spiral Call, I mean, all of us have had phone calls where you have to hang up and call again because GSM channels crack.
Yeah.
So have you done any work in trying to detect problems and when the signal was disrupted because of the phone system or when the prompt was caused by the individual?
Yeah, so we did some of that work. I haven't formally done a lot of that analysis, but what we were basically the kind of problems that might arise. So for example, there might be drop of signal in between. So you can easily detect that by just looking at the signal that you're capturing. And if a call drop happens, you can basically look at like the duration of the test and figure out whether the person was already, like how much of the air have they already exhaled and things like that. So I think a lot of that will be actually that if a problem occurs, then you try to basically figure out, not from like a development perspective, but from the algorithm's perspective that, okay, that doesn't look like the right thing, and you call back the user and tell them that do the test again. But yes, I've not formally evaluated a lot of those probability cases right now. And honestly, one of the bigger reasons for that is like recreating some of those issues in the lab is not that easy. Like we put it in like the anechoic chamber, we like put it in boxes, and I mean this lab itself is like this building itself is like as bad as it gets for signals, but still we were not able to recreate some of those things. Because I think what happens is that the call just drops. You are unable to get into a situation where parts of the signal are on or like there is noise and things like that.
So I'll ask from a semiconductor manufacturing background. If you had to change one of these sensors and improve some specific performance, which one would you pick and what the performance would be? So that's part one. And second question is, if you had a wish list of a sensor you could just pick and put in your phone and improve the results of what you can do, what would that sensor be?
That's a great question. So the I can sense my love. So yeah, so the first one, I'm really bad at this. I've done this so many times. What was the first one?
Sensor modification.
New sensors.
Yeah. So I think as I was saying earlier, right, like going beyond the perception of the humans and like adding some of these other capabilities to microphone, for example. Like right now we can use like up to 19 kilohertz, but imagine if we can go like to 15 kilohertz or 100 kilohertz. That might really help. Like, you can have dedicated devices to do that, but if you can just have them in the phone, I think that will be useful. And the other thing is like the other sensor. I don't think there is one sensor that you can pick which is say, you add this and the life will change. I think whatever is there, if we just keep on improving that and keep adding things, once we know the killer application for that sensor, I think that's fine. I think thinking of like adding one sensor that will do everything is not going to happen. I think even if some of those things are driven by the business model, that there is this killer app for this one thing and you add it, I think that's fine. Just providing the right amount of support for those sensors so that researchers and developers can use this, can be helpful. And then also understanding that, okay, we added this barometer, for example, into the phone, and it can help us in improving the GPS performance. But now that it's there, and researchers have shown that it can be used to improve activity recognition, then using that as a feedback loop and improving that sensor in the next or the next to next iteration can be.
Any more questions?
What are the possible threats that you are looking after in Spiral Smart?
In the Spiral Smart, I think from a research perspective, most of the like the research questions, like from a computer science perspective, I would say are answered to a large extent. But I didn't present any of the results for the clinical deployments. So that is one thing that is still an open question. The performance is reasonable, but it's not as good as we want it to be. So that is something that I still am working on. And the other thing is training people is insanely hard. Training them how to do it. You can train them in clinics and then send them back home and give them a device that go and use this and like to track their consumption is also very hard. So I think training is going to be a big issue with this, with the whistle or any of these designs.
Just to add another challenge to your work is that the signal becomes incrementally harder to detect with increasing obstruction.
Yes.
Because as you get more obstructed, you become more quiet during the first minute.
Exactly, and that's the main challenge that we are running into right now, right? Like the system works pretty well up to like 60% lung function, which is like a mild to moderate obstruction. But below that, the performance goes down very quickly because initially the algorithms were built on data from patients who had like slightly higher lung function, right? So when like the lung function is that low and the patient is really quiet, I think figuring that out is still an open question.
So if you think about, early on you talked about how you can leverage the mobile phone for interaction and for help. But what are your thoughts on kind of where do the requirements change where the phone doesn't really make sense at all? So obviously for life support applications, for for certain kinds of blood screening things, it doesn't make sense. But the things that could conceivably be on the phone versus a standalone device, like where do the requirements change where it doesn't really make sense at all on the phone? Like it's the barrier to introduce a piece of hardware or device is higher, but that diff is so much better. I mean, the result is so much better at the end of that than the incremental cost. So what are your thoughts there, and how do you see something like this feeding into a care system where you kind of graduate up to a more sophisticated or an additional device or something?
Yeah. So that's a good question, and the way I think of it is any problem that is rare enough that it doesn't make sense to have a dedicated sensor for that on a consumer device. If you can do that on a phone, I think that's reasonable because a dedicated sensor to that to the phone. So I think that's that's where the indirect sensing would be useful. But the other part is like, what if it doesn't even make sense to have a dedicated sensor on the phone, right? So I think any of the health sensing aspect, if you can do it on the phone, even by adding a cheap sensor, I would say is a fair game because at least in the low constrained environments, it's hard to get some of the expensive stuff. So if you can reduce the cost even like by one order of magnitude or even less than that, actually could be pretty useful. But if the condition is already very rare and detecting it is easy and cheap, then putting in the effort to add it onto the phone and making sure that it works across all kinds of phones and all of these conditions would probably not be as useful as some of the others.
I'm curious about your thoughts on Pokemon Go and like opportunities in the game industry for using sensors. With the side note that I love the problem that you work on, but just like.
So I don't have too much information about Pokemon Go because when it came out, I was writing this thing. I haven't started playing it, but I think the sensors that are there on the phone are incredible, right? Like they have a lot of potential, and it's just up to the developers whether they are making health sensing apps or interaction or gaming apps to basically figure out what we can do. And I think with like I was talking to, I don't remember, I think I was talking to Eric, and he pointed out that Pokemon Go is like one of the first examples of like a successful AR system. It's very simple, but it's still AR, right? So I think when things like that become popular, we'll start seeing some of the boundaries of the capabilities of these sensors to enable those kind of applications that will help us in pushing the envelope of the hardware. Honestly, chances of companies like Apple or Samsung making a change to the phone for Pokemon Go is much higher than Spyro Smart. So if they can do it, and then we can use it for the other applications that we do.
What about your thoughts on the intersection of gaming and things like spirometry for technique?
Yeah, so it could be really useful for incentive spirometry and training people on how to do it, for example. So yeah, that's a great point. Like for example, we are right now looking at examples where you use the front-facing camera of the phone to give the person feedback of how they are doing the test, why they are doing it. So if you tell them don't purse their lips, they might still do it. But if they see that they are pursing their lips on the phone right away, that might be a good feedback loop, right? So that brings in some of the augmented reality aspect to it. So yeah, I think there are enough overlaps there.
Any other questions? So back there.
So I wanted to ask about the feasibility of getting the whistles out into the developing world where they're actually going to be useful for improving spirocall. Have you given any thought into how you would actually go about deploying them?
Yeah, so yeah, that's a good question, and I think there are different approaches. I don't know which one is the correct one. So like manufacturing it at a mass quantities is not going to be expensive. There are no moving components there, so you can easily injection mold it for like less than 10 cents. But distribution can be a huge issue, right? So I think there are definitely challenges there. One thing that we have been thinking of, and this is driven more by Eric Larson, who is a collaborator on this project, and he's looking at like open sourcing the design, and then basically introducing it to like NGOs and things like that, and see that how it goes, what kind of traction can we get from that. So yeah, I don't know what's the right answer, but I think all of these options are open right now.
Yeah, Billycam has the same challenge with the calibration card.
Yeah,
Which is-
exactly.
It's a little piece of hardware that needs to be distributed.
But I think with Billycam, the advantage is that the babies are, like, and they're, or in many cases, they're in the hospital. So at least there is that single point in some measure of, in case of SpiroSmart, where the patient might not even know. And like, how do you diagnose that if they don't even get to the hospital?
It's not so much true in the developing world. I mean, a lot of
Yes,
first
yeah,
world-
of course. Yes.
Any other questions? Okay, so before we break for the just the committee only session, so I guess one last question I have is for the students in the room, what advice do you have for others doing application-based research? That's a good question, and I didn't get that in any of my interviews, and I'm glad. So I think the advice is to, like in some cases, implementing the system is much faster than testing it out like quite seriously. So I think that's very important, right? Like I showed a lot of stuff today, and like the initial part where I was talking about situational awareness, for example, I was really interested in taking that work forward. But at one point I had to decide that, do I spend more time on that or on SpiroSmart, for example? So I had that option, but even if, like you have that one thing going on, I think it's important to take it forward. And if you are interested in it, of course, if you're not interested, find something else. But if you're interested, taking it forward is important because getting that initial prototype, a proof of concept paper, can be quite easy at times. But making sure that it actually works and like figuring out those challenges can be very satisfying as well. Right, if there are no other questions, let's thank Mom.